Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Welcome back, fellow space cases, to Whimsical Wavelengths, the show where science is illuminated. Today, we're heading somewhere that never sees sunlight. And no, not caves, not the deep ocean, and not a professor's office during grant season. We're talking about somewhere truly extreme, somewhere ancient, quiet, and very, very dark. The moon. The last time this show talked about the moon was way back. Well, in the show's timeline anyway. All the way back to my first recorded interview. Wasn't necessarily the one that came out first, though. All about Lucky Peanuts in Season 1, Episode 6, with NASA's JPL's wonderful Dr. Morgan Cable. Feels like a different phase of the podcast entirely. And it's exciting. I get to mentally retrace that arc from those early Ranger missions, the tradition of Lucky Peanuts, and the sheer audacity of the race to launch rockets at another world, to where we are now. My podcast skills have evolved, and thankfully so has the audio quality. So let me pose this like a riddle. What's on the moon but never sees the sun? Well, there are likely lava tubes on the moon, but that's not what we're going to be talking about today. The answer is PSRs. I mean permanently shadowed regions. Near the lunar poles, there are deep impact craters that, with the moon's small axial tilt in reference to the sun, which is only about 1.5 degrees, those impact craters, the sunlight never reaches the moon's surface there. Ever. No sunrise, no sunset, no seasons. For comparison, the Earth's tilt is a comparatively large 23.4-ish degrees. That's what gives us seasons, solstices, and those long Arctic nights and days. The moon? Nope. Not in a solar sense, anyway. It's almost locked into the same lighting geometry throughout its orbit. So near the poles, where the topography and the geometry line up just right, the shadows become permanent. And in those shadows, temperatures can drop to colder than Pluto. One important wrinkle to mention here is that from Earth's point of view, the moon definitely does not look static in its orbit. We see changing phases, eclipses, supermoons, blood moons, and all of that drama. And that's because the moon's orbit is tilted about 5.1 degrees relative to Earth's. These differences in orbit lead to an 18.6-year cycle that over that time changes how the moon looks to us here on the ground. But here's the crucial part. From the sun's perspective, the moon is almost boring. Its tilt is only 1.5 degrees. The angle at which the sunlight hits the moon barely changes over time. There is essentially no seasons, no meaningful solar wobble. So while the moon may look dynamic and ever-changing from here on Earth looking up, in solar terms, from the sun's perspective, it's nearly frozen in place. And that's why these permanently shadowed regions stay permanent. For billions of years, potentially. Parts of those craters near the poles have remained locked in darkness. So today we're going to be shining a light, at least metaphorically, into the places where sunlight never goes, because it turns out some of the most exciting discoveries happen in the dark. Okay, please welcome someone who completed a PhD in 2020, is currently involved with lots of science communication and outreach, University of Maryland College Park Assistant Research Scientist at the Goddard Space Flight Center, and principal investigator of a NASA Lunar Stability Team on investigating decisions making under deep uncertainty for lunar exploration purposes. Dr. Katlyn Ahrens?
Ahrens, yeah.
Ahrens. See, I'm terrible at pronunciation. Welcome to be here. I'm so glad you reached out. So I guess a little bit of backstory is normally I poke people, cold call emails or through friends of a friends, but you actually reached out to me and volunteered to be on the show.
Yes, I found you out through colleagues on Blue Sky that have recommended other STEM type podcasts, and I'm like, oh, this sounds fun. And yeah, we figured it would be a cool way to talk about maybe some cool moon stuff today.
Yeah, and that's exactly why we have you on here, is to talk about the moon. We'll get there, but before the scientific paper at the center of this episode, there was you. And I like to do this in every episode, just kind of got to go back through how we end up in STEM fields, because a lot of people, especially in high school, they're like, oh my gosh, what do I do with the rest of my life? And it's hard to, some of us go straight shot like me. It was like, I'm going to poke lava with the stick, since I was like yay tall. And then other people come into it late. And I think we need to understand just how different people end up in these fields. So did you come into it like right away? You found it early? Or like, I saw that there was sources like an exploration, like you were in 10 years before obtaining the BSc. So I assume you found it quite early, like myself, and then just was kind of a straight shot, or was there some meandering there?
Oh, I definitely meandered for sure. So I was definitely interested in astronomy and rocks as a kid, but I found it more of a hobby. I joined a local astronomy club back in West Virginia at an early age, and just sort of grew up with the local astronomy club and just hanging out with space nerds for a while. But again, I only had a sense of it being a hobby. I honestly didn't know that I could make a career out of anything like this until much, much later. And so when I went to West Virginia University for my bachelor degrees, I was astrophysics, I learned radio astronomy, I was a radio astronomer for a few years, and that's all I really had in my mind of, oh, this is what astronomy is, this is what I should do, until I applied for an internship that had me do Mars geology, and my passion for rocks was always still a hobby. And then I realized, wait a minute, I can combine space and rocks to make this into a career? Oh my goodness, sign me up. So at the time, WVU didn't have space geologists. Now they do. Now it's starting to become a bit better with faculty. But at the time, there were no planetary scientists at WVU. And so how to start connecting with people outside of my institute was still very new to me. I'm a first gen college student too, so all of this was still very, very new and confusing kind of deal. But going to my first planetary conference as an undergrad really helped because then it's like, oh, I can now just tap into people's brains and go, where can I go with this? What can I do with this? Fell in love with it for that particular internship. That was back in 2012. And then it still took some meandering. I was doing Mars work, and then my PhD was on Pluto, much, much further out in the solar system. Now I'm at the moon, coming back into the solar system, and I still dabble. I still dabble with other planetary bodies kind of deal. I'm starting to get more into civil engineering on the moon and trying to tie in science and engineering too. So it's certainly been meandering, but that's the fun part then. And this is the advice I love to tell early career students out there is just have your own journey with this. There is no linear path to anything if you want to do space. We're very interdisciplinary. We have so many different people with so many different backgrounds that you pretty much slap space in front of it and it just sounds cool.
Absolutely. And in fair, I'm obviously from volcanology, and I have quite a few colleagues that have kind of dabbled on other planets as opposed to being their normal. They dabble outwards instead of slowly working their way back in. And I think we're going to have a future episode looking for Mars on Mars. Yes, I said that. MAARS, which is a type of volcanic eruption, and looking for those on Mars, which tells us something about groundwater. But I don't want to get too sidetracked. I guess time to pivot towards the moon. So listeners are probably aware of the moon landing. There isn't much in the way of an atmosphere, but perhaps that's where we should start. Does the moon have any sort of atmosphere, or can it hold on to anything?
Not particularly. So the moon does not have what we would perceive as a full, breathable, luscious atmosphere that the Earth would have. Instead, it has something much more transient. It's there, it's not, it's there, it's not. Called an exosphere. So think of it as like an exoskeleton for a bug. You would have an exosphere, a sort of outer thin shell of dust and plasma and volatiles. So itty bitty bits of hydrogen and carbon and oxygen just kind of migrating and bouncing around just very, very thinly all across the moon. Because as the sun is smacking up against the lunar surface, it's just exciting all of those different atoms, exciting to the point of burying that sunlight into the soil, and it's exciting all of those molecules up, and then they migrate. That's what we call it then, is just migration of hydrogen and helium and all these different compounds.
So what little atmosphere is there is actually being created by the sun exciting the chemicals within the soil of the lunar surface?
Yeah, that's most of it. The other part is the lunar surface, because there's no atmosphere, it's going to get bombarded a lot by itty bitty little meteorites. All of that can also help excite and overturn all that soil as well. So there's bits of rock, bits of plasma, bits of molecules just bouncing around.
Is there a way to, this is completely out of left field. I'm sorry about this. Just what comes to my head sometimes. Is there a way to look at the concentration of particles and then look to see how much has to be coming from space versus how much from the soil? Like how much volatiles is getting from micrometeorites and stuff like that?
So that's still very much an ongoing study because we're still learning so much about the lunar environment and also radiation too. So it's not just a one-sided problem with what's happening at the moon, but also the relationship with the sun as well. So like how much radiation is in this part of the moon versus this part of the moon. And you notice then when you look up at the sky, you have the really darker patches versus lighter patches of the moon. Each of those areas have their own mineralogy, their different geology as well. So topography is going to have a huge role in how these molecules are moving around and how much of it is retained into the soil. How deep does it go? So all of this is still very much ongoing investigations, which is quite exciting because understanding just the chemistry of what's happening at the moon can really help us out with resource management. Where do you want to go? What kind of science do you want to do at this part of the moon versus this part of the moon? So this is still very much an ongoing investigation.
Cool. So I guess just to follow on, because I can't leave it quite yet. What about being able to measure these things in real time? Like we have weather stations.
Oh, yes.
Do we have, I know we've sent probes, but I'm ignorant of what's on the probes and what still works. So, because it's also a radioactive environment, I assume it doesn't last too long. The electronics probably get fried over a certain number of years. But do we have quote unquote moon weather stations out there?
Not necessarily, but we do have quite a number of orbiting satellites going around the moon right now. So we have the Lunar Reconnaissance Orbiter that's been up since 2009. The Indian Space Agency also has the Chandrayaan orbiters as well. So each of these orbiters would have monitoring sensors as to what's happening in their orbit, some level of radiation. But for elements, that really does depend upon what you're looking into. So we have very broad, very basic hydrogen maps, neutron maps from Lunar Reconnaissance Orbiter or from other orbiter systems as well. We do have beautiful mineralogy maps from previous and current orbiters as well. So it's now piecing those together. What kind of minerals are you looking at? What kind of hydrogen concentrations might be around? We have iron concentration maps. But those kinds of maps when in orbit is quite low res. If you're wanting something a little bit more finer detail, this is where we're needing to send more landers, rovers, and humans.
Well, that's kind of what I was getting at. So you're describing remote sensing, which is You're remote, you're in orbit, you can do amazing stuff from orbit. We do it with the Earth too. It's amazing. But there isn't any, I guess, there isn't much for on the ground measurements of that exosphere, I guess, is where I'm getting at. That's like
Correct.
an avenue to come. Which I
It
think
is.
segues into the paper, sort of.
Sort of.
Because today we're talking about permanent shadowed regions on the moon. Diverse lunar, polar, permanently shadowed regions and environmental metrics for site planning decision making is the actual paper name. That's actually really well and easy understandable. Sometimes when we have papers, I read them and I'm like, I don't understand anything in that title. And it's great because we get to break it down. But that one seems relatively straightforward.
Good.
But nevertheless, there's still too many questions to ask. So I guess these regions make a moon base near the poles more ideal, at least based on my reading and the introduction at the beginning. So this is like how one would plan a mine if we were doing it on the Earth instead of like a moon base, because we're trying to think of where the resources are.
Pretty much, yeah. So referring back to like how those molecules migrate, right? There's certain molecules that when they migrate toward the poles, they really like dark and cold, because then they can just freeze together and just stay put. So permanently shadowed regions, as the name suggests, is that these are totally in shadow, where the sun don't shine, kind of deep and dark, mysterious craters at the polar regions of the moon. And so as these molecules are happily bouncing around the surface, la-di-da, if they find any of those deep, dark craters, they're like, oh, yes, excellent. And they'll snuggle in the craters and then freeze there. And so the exciting part is that we have remote sensing to tell us, oh, there's frozen volatiles here. It's mostly water ice, but referring to the paper title here, there's diversity in what kinds of ice might be in some of these poles. So not only are they dark, but because there's no sunlight, they're also very cold. We're talking as cold as Pluto in some of these regions, even somewhat colder than summertime on Pluto. So negative 400 Fahrenheit, you can get some really weird chemistry with some of those molecules bouncing around and then freezing together. So you can have water, you can have methane, you can have carbon dioxide ice. And so this is where that kind of diversity comes in on how did they freeze, how did they get there, and then everywhere is going to behave differently because topography is different. The depth and temperature of these craters are different. So that kind of lends into their chemistry is going to be different. So you can have one PSR that's maybe loads worth of water ice that we can use as a resource, and maybe the crater next door may only have carbon dioxide and only a little bit of water. And so this is where that kind of diversity comes into play, like which PSRs might be resourceful. How do we make sure that we know when we get there? And then how do we make sure we do it safely as well? Especially if we're using it as a resource. If you're there only for water, you kind of need to know where the water is. But maybe you want to know where the carbon dioxide is. Maybe you want to stay away from some of the really, really cold ones. You need to plan it out.
Okay, so you know the chemistries of these just from remote sensing from orbit?
We can have a pretty good guess. I mean, we certainly still need robotic systems to go there. We have, the upcoming Viper mission should hopefully help us out with that as well. The Chang'e South Polar landers as well has been super helpful to just have an idea as to what the environment is. We've never been to this South Polar region before, at least with humans. And so sample return, we haven't done this before. We haven't done sample return of what this ice really is. How deep is it? Maybe even just the physical state of this ice. It could be itty bitty, more likely it's itty bitty, little tiny ice grains. But is it like sheets and layers? Is it the crushed ice out of your refrigerator? We just simply don't know until we get there. So right now it's truly just inferring based on temperature maps and hydrogen maps, and we can infer the chemistry based on those.
Okay, that brings up two questions. Let's go with the chemistry question first.
Okay.
I would imagine at some point you're going through modeling to figure out what chemical constituents would be stable, right? I mean, you have to have some kind of physical basis to make this guess more than just the measurements from orbit as well, right?
Correct. So thankfully, there have been numerous studies from the 40s through the 60s on what ice can do, how ice behaves at really, really cold temperatures done in a lab. And so from those experiments from decades ago, we have pretty good ideas to, okay, if you're at this pressure, at this temperature, what chemistry might you be getting? How does it crystallize? Is it just going to vaporize as soon as you look at it? Is it going to take its time? Does it prefer depth? Does it prefer this temperature range? Some of those PSRs have some interesting temperature swings. So some of those volatiles may not survive very long in some of those dark craters versus others. So again, this is where kind of the where do you want to go and what do you want to what do you want to do? What do you want to do about it?
That's interesting because that's like the complete polar opposite, pun intended, to volcanology, because we do the opposite, right? We put under high pressure and high heat and then look at the chemistry changes throughout time. And you guys are like, let's reduce the pressure to essentially zero and the coldness as far as we can get it. So it's really interesting that you go literally the opposite to a volcano in a box. You're like, a PSR in a box?
Yeah, pretty much. I mean, and that's the fun part too, is we're still trying to figure out how do we do this on an experimental level as well. But this is also where we don't know that much about the soil mechanics on the moon either.
Right.
So like how porous that soil may be. Now think of it through volcanology, right? If your material of which a lava will mobilize, is it very dense? Is it porous? What kind of crystallinity are you dealing with? So you're having to deal with like your type of silica content as well. And in this case, it's how much of your carbon and hydrogen content is. That's going to affect your crystallization. What kind of pressure and temperature regimes are you dealing with to either enhance or maybe not of that crystallization process? So there's some
For sure.
fun physics similarities here with volcanology.
Absolutely. Diffusion's another good word.
Oh yeah.
Okay, and the other question, because this is more of a physical question, let's assume we get to the site and now you want to go sample volatiles that are in super cold environments. How are you going to get them back? Because it seems like as soon as you get them anywhere, they're just going to vaporize. And now, like, do you have to send a quote-unquote refrigerator truck or something that can keep them cold in their current status until you can get them analyzed? Like, what's the process there? That seems like a huge logistical undertaking.
It is very much a huge logistical undertaking, and this is exactly what is another fun investigation happening currently. University of Alabama actually just got a contract to help with that refrigeration system for cold sample return from the moon. They were just awarded maybe just last month, which is exciting because it's giving us that first step of, oh, right, this is as cold as Pluto. We can't just use any normal refrigerator because, as you say, exactly, the ice may actually sublimate and there goes your sample. So,
Well, not entirely. At least you get the chemistry, but you can't look at the solids or the chemistry, or like you can only get the gas, which isn't useless.
Exactly, which I mean, it can give you maybe half the answer, but how do you bring back a cold, very ice cold sample from a dark crater into the rocket to blast back up into space, to get through the screaming heated atmosphere of the Earth, to land, and then transport it into a lab? Yeah, it's totally easy. Yeah, sure.
That's crazy. I can't even. So I guess that's still in its mid stages. Planning
It's
that
still
out?
it's quite still early stages though, because we're still thinking about volatile sampling not until at least Artemis 4
Okay.
or beyond. So we're not ready, but it's good that the lunar community is thinking about it. There's a lot of contract work happening right now that is at least getting the preparation ready, and that's where we need to be.
Okay. And I guess this research that we're talking about today is also in some support of the Artemis missions, right?
Yes. So this goes into like site planning and making sure that we're careful as far as what environment are we really wanting to study here, because they're so different. Do you want to go easy and know we go to a place that we absolutely know that there's water ice? Water ice is very easy chemically. It's very forgiving when it comes to temperatures. So do we want easy mode more likely on the first sampling round, or do you want to go like expert hard mode, or we're going to get all the weird chemistry, we're going to go over here kind of deal? So this is more the latter part of this paper is just careful decision making. What kind of decisions, and we go through a bit of case scenarios, my team on this paper, on just, okay, if we were to do this, let's make sure we can get there safely. Can we sample it safely? A lot of these craters are very steep, so maybe it's more risk certainly for humans, but maybe not robotics. So this is where, again, the beautiful diversity of PSRs, how can we bring that into the fold of decision making and site planning?
Okay. Well, one of those diversity, I guess, jargon words that comes up is double PSRs. What is that, like double shadows? How do you double the shadow?
Pretty much, yeah, that's exactly what it is. Or I like to call them double troubles. So
That's what I call my kids.
Exactly. So think of it this way then: is you turn the lights off to go to bed, and it's dark in the bedroom, right? It's darker under your bed. So you're adding another topography on top of something that's already dark and make it more dark.
Because I guess the jargon word more darker is not better.
Yeah, I almost said that. Yeah.
So I guess there's a difference between the volatiles and solids and a double PSR because it's colder, right? Like that's part of the diversity that we were talking about.
Quite possibly. The problem with a lot of these double PSRs is that they're so small that it's really hard for a lot of the resolution of the remote sensing orbital data to really confine a lot of these. And so now at this point we're just inferring, going, well, we're pretty sure that this is where it can get darker, so therefore colder. But that's still a question about stability as well, because just because you're colder in this one part and all around you can get warmer, are you cold trapping? Are you just heating around it? Stuff is just going to escape anyways. We don't know yet.
Yeah, of course. And I guess just to be even more clear, because the analogy works so well, where double PSRs are inside a PSR, and it's like there's a little bed nearby that makes the double PSR, right? Like it's usually a part of a bigger PSR.
Exactly, yes. So that's the criteria, is that a double PSR would need to be within the original PSR.
So we've done a little bit of talk about concentration, where the stuff comes from, and how they're so diverse. So are there like, you've already mentioned that we're going to pick things based on how easy or hard the sampling goes and what we expect to get back. But is there also a difference in rates of accumulation? Like, how do we start planning forward for resources? Like, is this a self-sustaining resource on the scale of 10,000 years, a million years, a billion years? Like, what are we talking about rates in this regard?
Yes. So this is
You were way too excited for that question because nobody can see. This is audio only. They also can't see your T-shirt that says, "Can I lick it?" with the periodic table down below, which is phenomenal.
Thank you. Yes, no, I'm very excited about this because this is resource management question. And this is my cup of tea. So the thing about can we make this sustainable? Still goes into we don't know the physical content of this ice just yet. So again, like, is it crushed ice? Is it thin sheets? Is it itty bitty? All that stuff. But sampling it is certainly the first step to get an understanding of, okay, what did we do right? What did we do wrong? How do we make sure we don't just sublimate it to death? But then onward, absolutely. How do we do this sustainably? How, is there really enough for resource management? Is there really enough to make it into fuel, to make it drinkable water for future habitats? And so currently it's just like, we don't know yet, but it's some of those things that we need to start figuring this out now. And then another side branch to this too is, if it's not, then what? And so there's a lot of fun like risk scenarios that we can go into. My favorite though is, okay, say if it's not a viable resource, there's certainly maybe not that much as we thought there was, or maybe it would take so much processing just to get a milligram of water. Yeah, sure, that's gonna hydrate a platoon of 50 astronauts. No. But then can we maybe make our own moon water? Especially if it's a natural refrigeration system and just nice and cold, can we essentially bring and make our own? And so that can certainly open up a whole can of worms in that regard. But it does help save resources to transport, mass cost, everything, to transport all those bottles of water to the moon.
Right.
Can we just make and have our own, almost like a recycling water system on the moon? So that's certainly more ongoing investigations. But for resource management planning, like we love to go into like worst case scenarios and go like, okay, what ifs? What if we do find water and it's not enough? What if we do find water and it's deep? Okay, well now we need to figure out how do we build a bigger drill kind of deal. So it can get really fun real fast.
Okay, well, then what's the next stage to trying to figure out if you can engineer your way out of this if it is the worst case scenario? Like, I'm aware of, like, for instance, we have a pretty good idea of what the atmosphere on Mars is, so there is, like, plans that you could, in theory, extract carbon out of the air to create jet fuel. I'm not saying it's easy, I'm not saying it's simple or going to get you a lot of jet fuel, but there is a theoretical way to do it. We understand what that way is, even if we can't put it into practice. Is there something similar here? Like, do we have an idea of how much we could get in theory, or that it would work in theory, or what stage is that?
So it's almost to a near testing stage. So the Viper rover is going to be really exciting for us. So Viper is going to have a drill. It's going to have pressure sensors on it. It's going to have temperature sensors on it. So we're going to see just how fluffy or stiff the soil is. It's going to help us figure out volatile extraction as well. So as it's doing all this is going to give us an engineering idea of, okay, this is how tough the soil may be, or how easy and fragile some of these volatiles may be. And so having just that first step with the small Viper rover is going to be very, very easy for us. Well, I shouldn't say easy, but it's a first step to understanding, like, okay, how do we engineer this better? Because right now, if you were to just go like, I'm going to take my uncle's backhoe up to the moon and we're just going to dig it out and figure it out later, man, that's going to cause such a headache with time and cost, and you can just have a complete chaotic mess of completely destabilizing all your ice right then and there. So doing it carefully, safely with a rover first, get a sense of the environment, and then we can start scaling up to like, okay, this is how deep, this is how fragile. How do we do this?
Wow, it amazes me. Like, do we actually know more about this sort of stuff on Mars than we do the moon?
In current technology, yes, because
wow, that is wild.
Right? Exactly. It's because we've tested certain technologies with rovers and landers. And, what you were talking about with the oxygen from bringing in from the atmosphere, that's the MOXIE instrument. That was a first test of what we can do on another planet for oxygen just trapping. And so for the moon, even though we're not able to do that because there's no atmosphere, but having more technologies build up of, oh, hey, we're wanting to like stay at the moon. We're going to need more technologies here. And so a really big program that NASA is coming forth with is called the CLIPS program. If listeners out there are unfamiliar with CLIPS, this is a really exciting program. It's called the Commercial Landing Payload Services. And this brings about private companies and federal agencies coming together, partnering up, and building just these very small suites of instruments, just scatter them around the surface, of course in a very managed way, not just willy-nilly, you're going to land somewhere on the moon, good luck. But very much in a scheduled way. But each of them are going to have their own personalities. They're going to have their own sets of instruments to kind of get us really on the ball of, hey, not just going back to the moon, but we want to stay here. How do we do that?
Yeah, I wonder if there's an analogy here somewhere. We often say we know more about the moon than we do the depths of our oceans. I wonder if we can say we know more about Mars than our neighbor, the moon. At any rate, kind of going on, you said that Artemis 4 is the projected when we will attempt to sample permanently shadowed regions. So when can we look forward to that? Because Artemis 2 could have launched this month, but it's probably going to happen this year. So what's the timeline look like for 3 and 4? And what does, I'm ignorant, I didn't look this up beforehand. I probably should have, so I have no idea what Artemis 3 is supposed to do either.
Yeah, so Artemis 3 is slated to be no earlier than late 2028 right now. So we'll see how that goes. Obviously, that's very contingent on what we learn from Artemis 2. For listeners that may not be familiar with Artemis 2, we're not landing on the moon. We're just orbiting. It's almost like a dress rehearsal for Artemis 3. Because we've never been to the polar regions of the moon with humans before, we want to make sure that we can actually get there. So this is kind of the travel route planning kind of deal to make sure, like, okay, we got there, we angled it correctly, you know, how does landing gonna work for the polar region there. So, and then obviously how to bring them back. So Artemis 3 boots back on the ground after more than 50 years. Hooray, we want to get back to the moon. But still, we're going to a place we've never been to before, the South Pole region of the moon. So it's going to be some very basic testing. We're going to have pretty similar to Apollo style with like sampling, scooping, core tubes, core materials kind of deal. We're going to have a few instruments at the ready. A lot of them are toward the biology side. We want to make sure that, how our human bodies behave on the lunar environment. We only did that a little bit for Apollo, and now we need to be better. I mean, our technology has certainly been extraordinary since Apollo era. And so now we need to be like, oh, okay, if humans are going to be staying on the moon for longer periods, we should probably make sure that their health is going to be good, Yeah. So Artemis 3 is going to be exciting. Boots back on the ground. It's only going to be for a few days, but again, it's a start. Now, are they going to be doing anything with volatiles? Probably not, because our technology may not be exactly ready just yet. We want to make sure we could actually just boots back on the ground first and make sure we know what we're doing.
Come on, it's not so much that, is that we know what we're doing, but we need to test all the new equipment, right?
Exactly. I mean, we truly
mistake.
got some upgrades. We've really got a lot of upgrades since the 60s and 70s. So yeah, absolutely. But again, this is a whole new environment too. So even though it's like, oh, it's just the moon, there's no atmosphere. What's so different about it? It's like, yeah, but there's still some very big differences in the environment here, in the topography here. The soil here is slightly different. So I mean, there could be some interesting differences here. But then once we get that sorted out and we have a game plan, then Artemis 4, hopefully, supposedly, we're going to be a little bit bolder. We're going to go further into those deep, dark, mysterious places on the moon and maybe bring back a nice sample. That'd be great.
And that's pegged for what, 2030? something?
Yeah, 2030 something.
That's fair. I was just curious. So kind of this far, we've kind of talked about like a lot to do with the processes and a little bit to do with the data to like how we model it and stuff. But what kind of, you've already mentioned one, the lunar rovers that are going to go and make that chemical type test you mentioned. I can't remember the name of it. I'm so slow. But like, when is that going to happen? And like, what other data are you waiting for in the lead up to what is going to be in perhaps in your eyes, the holy grail of getting that sample back in one piece without it sublimating? Like what data, like...
Yeah, exactly. So through our conversation, we have a pretty good idea as to the temperature regimes that we're dealing with. We're dealing with what concentrations of hydrogen and neutron detectors, the mineralogy maps. That's all fine and dandy, but that's all still surface level. Now we're wanting to get more into the plasma environment. What kind of radiation are we dealing with? How does the radiation affect not only that migration of itty-bitty compounds that we talked about earlier, but also the human body? Could that radiation also affect machinery as well? So a big, huge pain of the moon is dust. By all means, it's a pain on Mars as well. We've lost rovers to dust before. Thankfully, the moon doesn't have global dust storms like Mars does, thankfully. Oh, goodness. That would be such a nightmare. But the dust on the moon is still very challenging for our instruments. So even just doing hour to day long experiments of that radiation and the dust environment would be really handy. But also back to the soil, too. So Viper... I keep saying Viper. It's a glorious acronym because NASA loves acronyms. This is the Volatiles Investigating Polar Exploration Rover. So it's about the size of a small car. So we're not strangers to car-sized rovers. We've sent plenty of them to Mars by now. But this one's slated to be about late 2027. But it's through Blue Origin, I believe, but it's gonna have a drill, which is gonna be exciting. About a meter depth of a drill, and then this is where we have no idea what's happening.
Yeah,
we need more information on the soil. How stiff is it? How deep is some of this stuff? Again, how sensitive some of these volatiles may be. We do have core materials sampled from Apollo, but in the South Pole with volatiles, it's going to be completely different environment there. But also for sampling in itself, if you have a human with a super duper scooper, you kind of need to know, do you need to like really push it in? Is it going to be so fluffy that it's going to be hard to contain? Do you need an extra wide super scooper? We don't know.
It almost harkens back to the original debate, like, what is the moon? Are we just going to land into a whole bunch of dust and sink, or is it hard and rocky? Like, nobody knew way back in the 60s during the Ranger missions. That's wild.
Exactly. And chatting with previous astronauts that have been to the moon, their best analogy is flour. So how flour, it's very dense, and you set it on the counter, a bag of flour, and initially, if you try to even just put a cup into it, it's a bit hard. You kind of need to jam like a measuring cup into it to get your cup of flour. But then all you have to do is just blow on it, and it'll get everywhere. And so that's the closest analogy that we have if you're trying to have a visual of just how hard and yet fluffy the moon can be.
Okay. I have in my notes here something I read, the shadow cam from Korea. Is this like to pierce into those PSRs?
Exactly, yes. So this was a very, very beautifully fancy camera that would just zoom by very up close to a lot of these craters. So it's still an orbiter, didn't land it anywhere. But what it did, though, was that it had a very specific filter to image the inside of these craters, because now that kind of goes into not just a morphology, geology, hey, let's see what the craters look like, woohoo, but also from a safety standpoint as well. This still helps with the site planning of like, okay, which craters may seem safer to land near and not
Right.
sink or fall into and freeze.
I never really thought about slope stability as like landing sites. I mean, that makes total sense. Don't get me wrong. It just didn't dawn on me to think like, yeah, we're gonna cause a moonslide.
It can happen. It can happen. There's some already some beautiful landslides all over the moon, so
Really?
it can happen. Yeah.
Can you
there's
like
some fun.
after this, as a total aside, send me like a paper that describes them? I would love to be able to read them, or I guess I could go on Google Scholar and find them myself now that I know they exist, because I never would have. We don't see as the average person like the moon is a very dynamic place. I mean, everywhere in the solar system is dynamic. It doesn't matter if it's Pluto or the moon, but it still seems stationary to us who don't study it, right? And so I'm surprised initially, but I'm like, of course there should be. I'm just not aware of it.
Yeah, no, the moon definitely was more energetic on a tectonic and volcanism scale.
Yeah.
You know, thousands to
About
millions
2
of years
billion
ago.
years ago, yeah.
Exactly.
Been a
Yeah.
while.
I mean, it's covered in really beautiful volcanic activity, and certainly landslides and so on. But absolutely, yeah, it's not something that we think of as being currently dynamic anymore, especially with like geologists on Earth, where it's like we see how active Earth is on a daily basis, and then for the moon, anything under 1 million years is considered young.
It's true. It's true. Kind of an aside before we start wrapping towards a close. We talked about PSRs, but we haven't actually talked about like lava tubes. So is that another avenue of looking for volatiles in the future?
Potentially. So in the south pole of the moon, there's not particularly lava tubes, but we're not just going to the south pole of the moon going forward with Artemis. We are still hoping to go to other locations around the moon to explore. So yes, absolutely. Can lava tubes be useful as a means of habitats or even just safe spaces, even storage as well, because they might be thermally stable. But it still goes into we need more data. There's been a lot of really interesting investigations about lava tubes, using Earth lava tubes and testing equipment for like field astronauts, or what we would like to call analog astronauts, testing equipment with Earth lava tubes. And can we get that kind of equipment ready for astronauts on the moon to use that same kind of equipment? A lot of that equipment is really exciting. You take like 3D scans of lava tubes and then convert that. You can use it with an Oculus Rift. And then can we then extend that to almost like astronaut training, exploration into virtual lava tubes as a sort of training before real life? It's really exciting of what all is happening right now to get us ready for that.
Yeah, it's amazing. Those LiDAR units can get down to like millimeter scale, people.
Yes,
They
exactly.
are truly impressive. And it's not just being used for space. It also allows us to digitize individual like features inside the lava tubes and study them separately. It's crazy what we can do.
Exactly. It's wild and really cool.
Absolutely. So I've almost kept you here for an hour. We're getting closer to that. So it's kind of time to start wrapping it up. Have we missed anything on polar shadowed regions that you feel needs a call out before we move to the less scientific things?
Just a short little call out here is that PSRs are literally cool, but also that there's still but that there's also still so much to learn about them on a not just a chemical scale, but also a geotechnical scale as well. Especially if we are wanting to use this as a resource, let's make sure that we are able to use it as a resource.
Yeah, for sure. All right, getting to the wrap-up phase. I wanted to go back to your bio because I didn't really want to do this at the front, and I wanted to get into the science because I was excited to talk about PSRs. But I think the rest of the curious people that are listening would also want to know about this Lego First League. Like, what? I had not heard of this before. What is it, and where can people find it? Because it sounds amazing.
It is such a really fun program. So it is both a national and a global competition sponsored by Lego, as the name suggests. So what First Lego League does is that it takes middle school and junior high students. You form teams, so different schools or even communities come together, you form a team, and you build robotics with Legos. And every year you're given a certain like checklist of challenges for your Lego built robotic to do. So not just physical challenges, but also there's a presentation side to it as well. And this is supposed to teach middle school and junior high students not just teamwork and building engineering skills, but also a cooperative professionalism. How do you communicate your STEM to an audience? And so that those two different aspects are really quite interesting, that it's not just build a robot and then that's it. There's different levels to this. So I was involved with this during grad school back in Arkansas, and I had never heard of this program either until there was a particular year. Every year is a different theme that revolves around like the challenge and what the student groups are supposed to be presenting on. And this particular theme, lo and behold, was on space exploration, specifically for astronaut health and technology. And I was contacted by...
Wow, they're that specific.
They're that specific. And I was contacted by a school that they were looking for a subject matter expert. And I'm like, I didn't know this program even existed. So I did some research in it. So then I became a subject matter expert for the greater portion of Northwest Arkansas. I visited nearly 20 schools all around that region, chatting with different communities, different school groups, because these students can reach out to scientists that if they need a subject matter expert to essentially help judge, like, are we talking about this correctly? Sometimes the students need to create almost like a product, even a concept of a product. In this case, for astronaut health and technology, that theme, they had to create a product that would benefit astronaut health and or technology. And this was quite exciting to see, like, what aspects were they going for? Are they talking about physical health or mental health, emotional health of these astronauts? So me being a subject matter expert, I just kind of gave them the groundwork of, you could go this way or this way or this way. Let's talk it through. Here's some resources that you can use for your presentation. Some school groups would practice their talk in front of me too, and I would give them feedback. So it was fun for them to kind of feedback from a scientist to figure out like how they can improve their communication skills, get them excited about presenting it in front of judges, and they get scores and they can move on into like regionals and nationals and so on. But yeah, every year is a different theme. You can certainly find more about it just by Googling First Lego League there. But anybody listening in that would be a subject matter expert for that particular theme, like, more likely there are going to be hundreds of schools nearby that may need a subject matter expert out there to just chat or just poke your brain a little bit. But that was very fun. I got to meet so many different groups, very inspiring, and I was awarded a mentor leadership award through that program as well.
Wow. I know this is blasphemous being from Canada, but I almost wish I did that instead of hockey. All right, so we're heading to the last question. Just before we get to the traditional, infamous last question, any final call-outs of any sort? That doesn't have to be science. It can be anything. It could be the next big STEM outreach thing you're doing. I don't know. Anything.
There's just all sorts of really cool projects coming up for the moon, and there it's not just science. There's also some cool engineering. lots of fun engineering tests that we're wanting to do at the moon as well. And we have quite a bit of fun, like seismometers coming to the moon. So yeah, there's all sorts of, oh yeah, no, I see you going there, yeah.
Well, I am a geophysicist.
Oh, there you go. Yeah, so I spoke your language there.
For those that can't see us, because no one else can, I was doing the whole Dr. Evil finger thing, like, yes, bring seismometers. Exactly. Okay, so the traditional last question. Tell us your favorite science joke.
I've been ready for this for weeks. Okay. Where is a favorite place that a pirate would hide their treasure on the moon?
I know it has to do with the letter R, but I'm not sure.
A PSR.
A PSR. You can't even see the X.
Exactly. See, it's the perfect hiding spot.
Awesome. Well, thank you so much for coming on and reaching out through Blue Sky. And yeah, I'm looking forward to it. And by all means, the next time you publish a paper, feel free to hit me up. We'll glad to have you back on.
Great. Thank you so much for having me.
And that brings our episode to a close. Thanks again for showing up and listening on. Remember, if you haven't already, subscribe so you don't miss a show. Tell a friend. Leave a rating and review. You'll be really surprised just how important those are to indie shows like this one. See you in 2 weeks.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's always colors weave stories painting the sky, swaying to rhythms as the galaxies fly by.